Hello everyone. In this session, I'm going to look at how we can really use random forests for survival data. Till now, we have used random forests for different kinds of data. One, when we had classification data, we have used the random forest for classification purpose, where we had a multi-categorical response variable, and we also have looked at a session where we had a classification done for a binary categorical variable. Now I am looking at using the random forest for survival data, and probably I am going to in the next session I am going to look at using the random forest for regression, which is modeling a numerical response variable. Here the response variable is a survival variable, which is more like time to survive. So we are modeling a time to event kind of a data, right? So that is where we can use the survival analysis. I would have a session exclusively dealing with how we can use the random forest for survival data as well. So the business problems again are these 4 or 5 different kinds itself, but the ways in which we can approach them, we have seen that we can use decision trees for working with survival data, and now we are talking about using random forest to handle survival data. So again, there is no one single measure or no one single algorithm which will be better than the others for all kinds of data. So that's the reason we are trying to learn as many algorithms as possible. We are trying to get a hold of as many techniques as possible so that we can apply all the techniques on the data with all kinds of flexibilities that each of these techniques provide, all kinds of customizations that each of these techniques provide. When I take them into R, I will try to create as many models as possible and test them out, evaluate them to see which model is doing a good job for the data that I have considered and use that for the prediction purpose. That is the major part of the supervised learning that we are going to do. So the same thing we are going to continue with the survival data analysis as well. Here I am going to take you through two major techniques uh, dealing with random forest for survival data. We are talking about a technique called survival random forest and another technique which is conditional inference survival random forest. So we will take the same data. Here the time to event data I am taking from the world of sports, from the cricket specific data. In the one day international games, I have picked up a sample or I've picked up a sample of games that are played by the Indian cricketer Virat Kohli. I've seen how many balls he is typically taking to get out. So the time to event here is defined as balls to out. Number of balls he is facing in games to get out. Can I really predict what is the kind of a probability that he will play for at least 50 balls before he gets out? So these kind of things I want to see based on various attributes. I want to link them to various attributes depending on the kind of opposition that he is playing, or depending on whether he is playing at home or he is playing outside India, or depending on whether he is playing in the first innings or in the second innings. So, like that, I really want to understand the time to event, which is the balls to get out. I want to model typically the balls he would be taking to get out in a one day international game based on these various attributes. So because it's a time to event related data, I want to use the random survival, I want to take it as a survival data. Here instead of time to death or something, we are taking balls to get out. The time we are measuring in terms of number of balls he is typically facing. Let me look at the data, the characteristics of the data. I have just loaded this data out here. If you look at the dimensions of this data called Virat, so there are 168 rows and 7 columns in it. Let me just check what is the content of this. You could see here the ball space. This is the time to event kind of a data. So in the first game, he faced 22 balls and then he got out. And I want to check whether I can link this time to event, whether based on the strike rate or position at which he is coming out to bat, the innings, whether it's the first or the second innings, the opposition against which he is playing, whether he is playing at home or away from home, and the status is talking of whether he has got out or not out. One is that the event has occurred, which means he has got out. Zero means the event did not get occur, which is like a censored kind of a data in the traditional survival data analysis terminology. So zeros indicate that he was not out. So this is what I would like to model, right? So looking at things just to make sure that the data is not abnormal, I am looking at the summary of it. So the ball space we had anywhere between 0 to 148. The strike rates is looking like a text, right? Strike rate is looking like a text 066.66. So better I should look at what is there in the strike rate so that I can remove. There might be a one or two text elements in it, so it's better that we get rid of those text elements. So that's where I'll say Virat $SR. Let me just look at the values. So somewhere there is a hyphen. So it's better that I get rid of that hyphen from the data so that all other things are handled properly. So I'll just say Virat, I'll update the data where I am taking the subset of Virat, right? Wherein the rows that I would be considering is Virat $SR is not equal to this hyphen. So I will consider only those rows where Virat $SR is not equal to hyphen, and I would consider all the other columns. So based on this, now if I quickly check if my objective is fulfilled or not, I will look at the dimensions just to see if the dimension got slightly lesser. Yes, earlier it was 168 rows and 7 columns. Now it looks like 167 rows and 7 columns. And now I have the flexibility of making the summary Virat $SR. I can very well convert it into a number. So I'll say as dot numeric, as dot character Virat $SR. That's how we convert any kind of factors into numbers. So I am converting that into a numeric. So now let me just check the summary once again to make sure that the summary, yes, The minimum is 0, the maximum is 209. So we have the strike rates operating out here. The positions, he has batted right from position number 1 to position number 7. So I would like to understand. So this one, if possible, I want to convert this into a factor because the positions are very, very discrete rather than a continuous. So he might bat at 1, he might bat at 2, but probably I can convert them into a factor, or I can retain it as a number so that my decision would come out as less than or equal to 3, which means batting at 1, 2, 3 positions, something like that. But if you want to be more specific, I suggest that you can convert position as a factor as well. The innings, the innings also we can treat it that way. We can convert it into a factor, but nevertheless only 2 innings are there, so it doesn't matter too much. The oppositions, yes, these are the various oppositions against which he has played. The home versus the away, this is the kind of scenario. Status wise, zeros indicate that he has got out, 1 indicates that he has not got out. So we'll use this data for building our survival random forest, right? So let's get into the random forest understanding. So this survival random forest is actually built using this particular package, random forest src, and we are using the function rfsrc, indicating again a survival random forest src, right? So we can very well install the package random forest src. Random forest src. Okay, the package needs to be installed first. Survival analysis requires another package also called survival, right? Apart from this also requires another package called survival, because I have to combine from the data, I have to combine 2 columns. One is the status indicating whether the event has occurred or not. In this case also we had a column called status, which was saying whether 0 means the event did not occur, which means he is not out, and 1 means the event has occurred. So 0 indicates that the event got censored, that means he is not out, and 1 indicates that the event has occurred. So this is what is one variable I have to consider, and the time that is taken for the event to occur. These two I have to combine and create something called a survival object. That would be the input for the survival random forest. Right? For that purpose, any survival analysis kind of model. So that's the reason I would need to load even the survival package as well. That is the one that would convert the data which is time related and status related. Both of them are combined to form a survival object. Okay, let's see the installation. Let me just check. It has actually given me an error. We need to see why it did not work. Looks like now it is getting installed. Now the package is installed. Let's load the package. Let me load the package library random forest src. Okay, this package is loaded as well. Now we should also load the survival package, library survival. Alright. Now we also need to understand the function rfsrc. That is the one that is being used to build our random forest, survival random forest. rfsrc. Let's try to understand what is there here. So, random forest for survival, regression and classification. That is what is RFSRC. So again, a random forest is grown using the supplied training data. So we have to provide the data to it. So applied when the response is numeric, categorical or right censored. So here we are having a right censored kind of a data. And it yields regression, classification and survival forest. So I can very well use it for survival random forest, or this model I can use it even for regression as well as for classification also. Right? Now we will try to look at the survival random forest usage here. The first thing is I have to give the formula, right? The formula wise, if we see here, it's a symbolic description of the model to be fit. If missing, unsupervised splitting is implemented. Now, if I have to really give the formula here for the survival, this should be the response variable should be a survival variable, and then I should provide a set of independent variables. So I have to make sure that the original data, which contains the status as well as the ball space, both of them are converted into a survival object. I have to give the data, then I have to specify how many trees I require as a part of the model, and whether again mtry, number of variables to be tried randomly at each of the trees. How many variables do I need to try by default? The kind of importance, whether I require to display the importance associated with each of the variables. I am also interested in finding how many splits, n split, non-negative integer value. So when 0, deterministic splitting for an x variable is in effect. Maximum number of n split points are randomly chosen among the possible split points for the variable. So I can very well say n split, number of splits to be either 3 or 4 or something. That's one more important thing that I can give as an input. Proximity, I can set it to true. Importance, I can set it to true. Again, we have different types of importance that we can get. I'll talk about them later. Right, if you look at the importance method for computing the variable importance. Right, these are different kinds. By default, when I'm setting it to none, it means that the variable importance is typically not computed, but I have various other methods to compute the importance of the variable. So that's how I can give as an input to this particular model. So we can get started using the fit method. So I will say fit RFSRC is the name of the function that I'm using. The model that we are using is survival. The independent, now I have to give the independent variables here, which is the time. The survival as a function, the serve as a function requires two important stuff. One is the time related. In our case, the time is the wall spaced, and the status for us is the status itself. So these are the two inputs that I have to give. That is what will create my survival object. This survival object, now I have to talk about the independent variables or the explanatory variables that would be influencing this survival object. So based on the strike rate, can I make out how many balls he is going to take to get out? Or I want to look at it based on the position he is coming to bat. I want to look at based on the innings, whether it's the first innings or the second innings that he is playing. I want to see whether the opposition that he is playing against will determine how many balls he is going to face or how many balls he is going to take before he gets out, and finally whether he is playing at home or away. So this survival object is the explanatory variable, is the response variable. These five are the explanatory variables. So we are trying to build a model with that. The data that we are considering here is Virat. Of course, I did not break the data into the training and the testing. If I want, I can very well do that, because I can very well do the testing of the model as well. So let me see, there are 167 rows altogether. So 0.7, 70% of it is approximately 117. So I will set a seed value for 1000. Then I'll create a variable called train, where I'm sampling between 1 to 167 some 117 values randomly, where I'm setting replace equal to false. So this is my train. So based on that, I'll create my train data, which is again a subset of Virat, which will contain the rows that are there as a part of the train, and it will contain all the columns. Similarly, my test data is again a subset of Virat, which will not contain the values that are there as a part of the train. It will contain all the columns. So I have my training data and testing data in place. Based on the training data, I will go ahead in terms of fitting of the model. So I have a survival, RFSRC is the name of the function that I am using, where I need to create first the response variable as a survival object. The survival object is getting created using the ball spaced and the status. So these two are the variables. The status has to be 1 if the event has occurred, and 0 if the event did not occur, and if some censoring has occurred. And the independent variables, are the explanatory variables that I am considering in this context, are the strike rate, the position at which he came to bat, the innings, whether it's the first innings or the second innings he is batting, the opposition against which he is playing, and home versus away. So this is what is the list of the explanatory variables with which we are going to build the model. I know the data is trained data for me. Then, as a part of the model, a few more things that I want to give. Number of trees, yes, by default it's 1000. I'll retain it at 1000 itself. If I require some kind of a bootstrapping from the original data itself, I can very well do that. Okay, mtry. Mtry, I can very well set it now that there are hardly how many? There are hardly 1, 2, 3, 4, 5 variables. Square root of 5. So I should try mtry as 2, the default behavior. Then node depth and all, if I want, I can set the number of splits. I can set it to 2 or 3 so that multiple starting points are typically being looked at. I'll also set importance equal to true for this particular model so that I'll get the importance of the variable, which variable is contributing heavily to the overall process. Then all these things I can very well ignore. So let's build the tree with this information. Let's build the random forest, see if things are working out, and then if required we can improvise the situation as well. Yes, the model got fitted, and if I simply type in fit, the name of the model, this is how it came out. So the sample size is 117. When it is saying number of deaths, number of times the event has occurred, number of times the outs have occurred in this 117, it is 98. I've built 1000 trees. The minimum terminal node size is 3, right? And average number of terminal nodes that came out is 36. Number of variables tried at each split mtry is 2. Total number of variables are 5. So random survival forest is something that it is fitted. So these are the number of random split points, 3, error rate. Finally, in the training data, the error rate came out to 22.72%. So this is how it worked out, the fitment. And even if you are going with a summary of fit, in the summary it is giving us all the things, whatever are the various outcomes that have come. It has listed all those outcomes, so there is nothing much for me to understand from the summary. But when I am doing the plotting, this plot has given me a slightly a different stuff based on the number of trees. If you see, irrespective of number of trees right from 0 to 1000, the error rate has been remaining very stable. The error rate, we did not see anything increased or falling or something. The error rate has been more or less stable for the different number of trees. You could see importance wise, the strike rate is carrying a very high importance out here. The position at which he is playing having the next layer of importance. The innings in which he is playing again having a very minute importance. The opposition, home versus away, is having a kind of a negative importance overall. So that is how the importance, when we are going with the fitment, it has finally worked out that the strike rate is having a slightly higher importance, and relative importance wise, if I am taking it as 1, the others are having very minute kind of importance in the overall scenario. Now I can use different kinds of mechanisms to understand the importance of the model. Right, if you look at the model, we have different types of importance. I can set it to either permute, or I can set it to random, right? So I can get the importance from any of these mechanisms. I can set it to permute ensemble. I can set it to random ensemble. So I have different kinds of things that I can very well set to understand the importance of the model, right? So we will try out all those kinds of importance, which I can even execute using the vimp function, right? So let's see the importances that are associated with each one of them. So I'll use a function vimp where I'm using my fitted model. So look at this vimp function, which is talking about the variable importance. Calculate the variable importance for a single variable or a group of variables for a training or a test data. So all you have to give is the object. The object is the random forest object that we have created, and the importance I can set it either to permute or all these things, right? And I should the output wise I'm going to get the error rate as well as importance. So when I say dollar importance or dollar error rate, I'm going to get the OOB error for this as well as the importance of each of the variables. So I can simply leave that as well. So I'll say vimp, right? I'll use my model fit and I'll set importance equal to, let me set it to permute, the first one. Let me set the importance to permute. So this is how I am getting the variable importance. You could see here when we are setting it to permute, right, we are able to see that the total error rate is around 22. And okay, I need to give dollar importance also, otherwise I am getting only the error rate. So let me give dollar importance. So this is where I could see, even in this case, the strike rate is having a very high importance, and followed by position, innings, and so on. Now I can very well change the next one. Instead of permute, I'll set it to random, just to see which one is having a much lesser error rate. So when I'm setting it to random, the error rate is still 22.72. More or less, I could see that the process is more or less the same, right? And now even when I'm looking at the importance, the variable importance, I should see that the results are more or less the same. Here you could see 17.33, 17.26. Position is having a slightly higher weightage than the innings, but yeah, opposition is having a slightly better weightage out here compared to the innings, and home or away is still carrying that negative itself. That is from the random perspective. Now when I go with permute dot ensemble, I can try out all of them to see if there is any kind of an improvement in the overall error rate of the model. I don't see that error rate is getting impacted in any case. So the only thing is the importance factor is changing a little bit in all these things. Here also it looks like the strike rate is coming out very high. Next comes the opposition in this model, whereas the position is coming third and the other two are having a negative kind of an impact. So like this, you can actually look at all the possible importances, see in which case the error rate is improved, and also you can check in which case which variables are really playing an important role in the determination of how many balls he is going to take before he really gets out. So we have created the necessary data, we have loaded it, we have created a survival object, We have done the preliminary inspection of the data. In our data, actually, there was one variable which was a text, but we converted that into a numeric by removing the hyphen that is present in the text. We have split the sample data into a training set and a testing set. We have identified the response variable, which is a survival variable, and we have identified the series of explanatory variables. We have estimated the random forest using the training sample, and we have used the function RFSRC to do that estimation. The number of trees we have set it to 1000, but again we have a flexibility to change the number of trees. And number of variables randomly sampled mtry we have set it to 2, but again we have the option to change the number of variables that you want to try at each of the splits. Then we got the error rate, right? We have plotted the error rate with the number of trees. Here it was more or less constant at around 22%. Variable importance we have seen, strike rate is playing a much higher role compared to many other variables in the determination of the time to occurrence of the event. And we have also got the variable importance using different kinds of methods which we have used as a part of VM. Then there is another way. I could also use var.select method, right? I could also use var.select method to assess the importance of the variables. Again, for the same objective, let's just quickly look at what is there as a part of var.select. Variable selection using minimal depth. So again, I am providing the formula, or I can directly provide the object. So I can directly give the object of the class random forest src, right? If I am supplying the formula and the data, I don't need the object. But if I am giving the object, I don't need the formula. So I'll give the object, which is my fitted model. And there are, if you see, by default mtries and all those things are taken care of. But methods, we have three different methods. Here, minimal depth, MD is standing for minimal depth method. VH is variable hunting, and variable hunting with VM, variable importance. I can have these three kinds of methods to typically understand what is the importance that is associated with each of the variables. So I can very well try this out. var.select, I'll set my object as fit, right? I'll use my object as fit, and method I will set it, let's say, as MD, just to understand what is the importance of the variable that is coming out here. So this is how the importance of the variable is computed. You could see here it's a minimal depth variable selection. We have 5 variables altogether. We have set the number of splits as 3, mtry we have set it as 2 for this model. The node size is 3. Then the model size is 5. The depth threshold is 3.92, and the true OOB that is coming out of the bag error is typically 22.72%. And the strike rate is having the error, importance of 17.2, followed by position, then the opposition, then the innings, and finally the home versus away for this person. The same logic I can experiment. Instead of MD, if I want to go with a variable hunting kind of a method, I can say VH. So when we are trying to identify which variable is important using this VH method, Okay, so this is how the process is going on for the VH method. The true OOB rates in some cases they are falling down drastically, came down to 20 here, 19 here, but in some cases this has gone up even to the extent of 40s and 50s as well. So now going with all these kinds of iterations that have been done as a part of the variable hunting, this is doing a completely different job. If you see, the depth ratio is 0.21 in this case, but it has come out with the PE, which is the out of the bag error of 39% plus or minus 15. So it might go to down to 24, but again there is a possibility of almost 54% coming up as a part of the out of the bag error estimate here. And you could see the top variables that are contributing are strike rate and the innings itself, whereas all other things are not going as such as the important variables contributing to the survival part. So like that you can very well play around with the different kinds of approaches to really get an understanding of which variables are really contributing to the survival and which of them are not contributing. Then once you have understood that, you could also get into the understanding of the interaction effects between the various pairs of variables. Right? I have taken 5 different variables in the model. Explanatory variables, we have taken 5 different variables, and it will take all these variables along with their combinations. So based on that, when I am using this function find.interaction, where I have to provide the variables that I am going to consider, and again the method. So if you really look at this function find.interaction, so if there are some kind of interaction effects between the variables, this would give me the kind of this would give me a kind of understanding. So variables independently may or may not be contributing, but two variables taken together, they are contributing to the survival of this particular object, or survival of this particular person, or the probability of this person getting out. So this is where I can give find out interaction, where I have to specify the name of the object, which is my fit, which is the random forest object that we have created. I could also have to mention the number of variables that are going to come into the process. Method wise, we have two important methods. One, the maximum subtree, or the VM, which is the variable importance. Importance I can set to any of these different importance mechanisms, and I'm also setting the number of variables. The number of variables I am setting it, this number is very much required. The number of variables var, I am setting it to between how many variables the interaction effects need to be found out. So this is what I have to give as a part of my input. So let's say I am saying find dot interaction. Right, let's check what is happening here. The model that I am considering is fit. The number of variables in my case is 5, so I am giving all the 5 variables. And when I am talking about the method, I can have either the max subtree or the vimp. Let's say I'm considering the vimp method. Again, we have a flexibility. We can change it to maximum subtree kind of a method as well. And let's say I want to find out the interaction between the various. So there are different pairings that are happening. SR is being paired, strike rate is paired with position, innings, opposition, home away. Similarly, position is paired with innings, opposition, like that. All the combinations are being tried. Number of paired interactions is 10. And based on that, if you see, this is the variable 1, this is the variable 2. Individually, the importances associated with them. And this is the paired variance. When they are combined together, this is the kind of importance that is coming out for them. So the additive versus the difference. We are looking at these two aspects. When I'm adding that, right, when I'm adding these two things, it's working out to be this much. Versus when I'm up, once I have added, I'm looking at the difference between these two, which is resulting in this much. Now, how do I interpret this? Take the number of variables to be used. So we have 5 variables. We have chosen the method as vimp, variable importance. So importance of each variable is calculated individually along with their paired variable importance. So the paired variable importance is coming out to be something like this. Sum of the two values is known as additive importance. So we have added variable 1 plus variable 2, which has given me the additive importance. And now there is a difference that is being computed between the paired and the additive. So I am seeing in many cases the difference is negative, right? So if the difference is positive, it means the interaction is giving me a much higher importance than the two variables individually. If you look at this strike rate versus innings, the difference is positive. It means that compared to two variables individually, variable 1 and variable 2, which is strike rate and innings individually, their pairing is giving much more higher importance compared to they existing individually. So that is an indication of an interaction effect. So a large positive or a negative difference indicates a potential interaction provided the individual variable scores are large enough. Whereas here the individual score is not that large, so I am not taking it seriously, but that is what I am trying to showcase it to you. If the difference is very positive, it's an indication that there is an interaction effect between the variables. Even if the difference is highly negative, also I can talk about a combined interaction effect that is present between the variables. So this is how we can actually go ahead and do one more level of analysis in terms of assessing not just the variables independently, but I am also interested in checking out if at all two variables combined together are having any kind of an influence on my survival object, right? Now, once I am done with all these things, I can do the prediction with respect to the test sample. So let me simply say pred. I'll use the predict function. The model is fit and the data that I can take is my test data, and obviously the test data will not I can take my test data directly. Okay, the model is fitted. Let me just check the pred. So based on this, here you could see the pred wise, the error rate on the prediction is coming out to be around 25.49%. That is how the prediction part is coming out. The error rate associated with the prediction is coming out to 25.49%. If required, I can go with the plotting of the spread, which will give me the error rate is somewhere here, which is constant across all the trees. And I could also look at the plotting of the survival object, right? Plot dot survival. If I'm doing of this spread, I'm also going to get my importances of each of the variables, or probably I should do a first, let me do the plot dot spread, plot of prediction itself. So this is one thing that I have got, which is the error rate. Okay, this is the error rate that has come, and I'm also looking at the survival plot dot survival of spread, which is giving me some information regarding the survival part. So as the time, here the time is with respect to number of balls. So as the number of balls are increasing, this is how the survival, which is staying at the crease, remaining not out, is typically falling in this kind of in this kind of a model. And the actual mortality versus time, mortality is the getting out, is actually showcasing this kind of behavior, wherein you could see the black ones are the ones where he has remained not out in the process. So that's how we are looking at both the training as well as the testing data. What is the probability? So these are the this is the most probable kind of a line, and these are the ranges in which that probability could typically lie. So if I have to talk about the probability of facing at least 50 balls, I could very well take this 50 out here, take it to here, and say that it's around 40% or 40 to 45% that he will be facing 50 balls without before getting out. So like this, I can very well do the comparison, and based on that I can give my decision with respect to how many balls he can survive given this kind of a data, right? For each of the observations, this is how we are able to compute the survival time to survival using this survival random forest model. So that's it regarding the survival random forest. Then we are going to look at the next model, which is going to do a similar kind of a prediction, similar kind of an outcome on the similar data set, which is we will be using the survival random forest. We have seen that the error rate in the earlier case is to the extent of 25.49% on the test data. I would like to see the same, whether it is better or worse when I am taking it into a conditional inference survival random forest, right? Now moving on to conditional inference survival random forest. This is executed with the party package, and we have the cforest function. Even earlier we have used this for classification as well. The same thing we would be using for the survival function as well. So that's the reason I don't want to go more and more deeper in terms of explaining the cforest. We have already had a detailed explanation of the cforest function earlier. So let me load the package directly. Library party. And cforest for a quick understanding. So I have to specify the formula here. So in the formula I will be talking about uh, the survival object as the response variable, and all the other things as the independent or the explanatory variables. Data wise, I can give the data frame, right? And the controls. So the controls was something which we have used earlier also in terms of controlling the number of trees, or specifying how many variables should be used as a part of mtry, All those kinds of things we are controlling through the various controls. So based on that, we should be able to fit the model, right? The controls are very, very important. We can very well look at the controls from this particular section, wherein I can talk about number of trees. By default is 500. I can set it to 1000. Mtry by default is 5. I can set it to 2 because hardly I have 5 variables out here. So some of these changes I can very well make, right? So that's how I want to go ahead in terms of fitting this model. So let me call fit, wherein I am using the cforest function. Here my dependent variable should be a survival object, so that's where I am using the survival function, right? I am using the survival function based on the ball space and the status. So this is my survival object. Till day I am taking the variables. So the variables means, yeah, we have here. Let me take SR, POS, INNS, SR, POS, INNS, opposition, home, away. So these are the 5 variables for me. The data is coming from the training data, and I can set the controls now. So this is where let me use the controls. So I can use controls is cforest underscore unbiased. Out of this I am going to set within the unbiased. I have to decide what all I would like to set. I will set entry equal to 1000 and mtry, let me set it to 2. By default it is 5 there, but because the total number of variables that we are having itself is 5, better let me go with 2. So this is how this model got fitted. Let me have a quick look at this model. So this is saying that there are 117 observations. These are the inputs that it has taken and it has built the tree. And if you are looking at the summary of this fit, there is not much of an information that has come out from this. And if you are looking at the plot, these kind of functions, the plotting also would not be possible. And if you are looking at the structure of this fit, there are a lot of things that are coming as a part of this particular object. So these are all the things that have come out as a part of the structure, right? We have got the weights, we can access any of these things through the dollars. Okay. Now you could see here the survival function got created out here. The transformations being performed. So I can see if I am getting attributes of this fit. There are so many attributes that are coming out of this fit. There are slot transformations being performed. This is the survival function. This is the predicted transfactor, which is the survival ball space. So these are the various attributes that have come out. Now what I can very well do is this model I would like to I would like to use it for the prediction purpose. So I'll say pred. I'll do the predict of this particular pit, and I am using the test data for the testing purpose, and I would like to go with type is probability. Right, if I don't set that type as probability, let me just go ahead with it. So it is invalid. Right, the type, the fit and the test data, and if I am setting the type equal to prob, so error in OOB and is null of new data. Okay, so I think I have to specify the new data equal to test data. Yeah, I have to specify the new data as test data. So let me just see if I omit the type, what is that I'm getting. Just let's look at the pred. It tells me that for each of the observations, as per the model, this is the time for survival. Right, the pred is saying 2, 20, 24, 27 and so on. So this is how the survival is typically. Okay, for the record number 2, 27 is the survival. Record number 20, 73 is the survival, and so on. Now if you look at the actuals, test data, the actuals, if I'm looking at test data dollar wall space, so these are like this. So this one is 67, but here it is coming out as 27. Then it is 73 out here. Here it is 71. Here it is 29. Here it came out to 95, and so on. So that's how the values are typically coming out. The actuals versus the predicted. Right. So this is what is coming out through the predicted. This is what is coming out through the actuals. And I can also look at the type equal to prob. The type equal to prob has actually brought in for each of the records. Now if we see, going back to the first record, the record number 2, right, and these are the event, the median is 27, so it has been able to predict it as 27. The survival time, for according to this model, for the second record it is 27, whereas in reality it has worked out to 67. Similarly, for the second it came out to 73, the prediction is around 71. So in some cases the prediction came out to be much better, whereas in some cases there is some level of error rate that is existing. So this is where I can typically look at the predicted values. I can look at the predicted values of each of the patients, of each of the performances with respect to the time, and based on that I can very well go ahead in terms of the representation of the stuff. So probably if required I can go with a plot wherein I am taking the first record pred. I'll take, let's say, the first record. I want to do the plotting of that particular person, but of course because across we are seeing that the numbers are more or less the same, so we could see that as the time is progressing, this is how the overall function came out along with the 95% intervals as well. As the time is increasing, so this is how I could see how his getting out is very much possible. The probability that he will stay for 60 balls is somewhere around here. The probability that he will stay for 100 balls is around here, and so on. Whereas when I am looking at the record number 2 from that prediction, I see that the graph is slightly different. So like that I could check for all the graphs. The record number 3, again I could see that the chances are completely different, the probabilities are completely different. So here we are talking about a Kaplan-Meier curves for each of the individual performances. So I could really relate each of these things to the patient, and for each of the patients we can think of how this patient is going to survive at the end of each of these periods. So here for each of the balls, I'm talking about each of the performances or each of the matches based on whatever is the data that we have come across. So because we already have the actuals for it, there is nothing much for us to talk about. But when we are talking about a new record for which we don't have the output, this is how we can understand each and every performances related survival model. So that's how we can use the conditional inference survival random forest. I think we have done this entire process. So we have got the conditional Kaplan-Meier survival curve for each of the individual records, right? So if I have a new data altogether for which I don't have the time to event kind of a data, in that case, this would be extremely useful for me. So for that purpose, I am using the prediction part here. I have just tested it out with the testing data, but when I am using it for the prediction purpose, what I am going to get is this particular person, when we are talking about this opposition, this being the strike rate at which he is playing, are probably these are this is the innings, first innings or second innings, home versus away. If I give that kind of an information, I can talk about what is the probability that he is going to stay for 50 balls, what is the probability that he is going to stay for 100 balls, and so on. So that is the way how I am getting the plotting of the entire graphs for each of the individual records, which is what is going to give me a good understanding of which variables are really contributing to the model and which variables are not contributing to the model altogether. So that is what I wanted to talk about, the usage of random forest for survival data. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.